Welcome back to Math and Beats. Another video, and this time we're going to do an example of how to use a contradiction to prove a statement. Let's go. Here we go. Proving a statement by contradiction. Okay, so just to recall, contradiction is an example which falsifies a statement which was previously thought to be true. And to see how this works, what we're going to do is we're first going to construct the truth tables for the logical implication if P then Q, and then also this other one over here, P and not Q. So if that, then this other statement C, where C is a statement which is always false. Hence, contradiction by definition. So you might be wondering, why are we going to look at this if P and not Q, then something that's always false? Well, we're going to see in a minute. So we're going to go ahead and construct the truth table for all this stuff. And here we go. I got the truth table already constructed here, at least the headers. So let's go ahead and fill in our P's and Q's. P true, Q true, P true, Q false, P false, Q false. Actually, P false, Q true. Let's do that one first. And then false, false. Let's negate Q. We'll need that in the the second statement, that one right there. So not Q, just negate everything in the Q column. False, true, false, true. And now we look at P and not Q. So we'll look at these two columns right here. So that thing is always false except when they're both true. So the first one, true and false, is false. Next one, true and true, that's true. False and false is false, and false and true is false. So only true when P and not Q are both true. Now for this statement C, well, we're assuming it's always false. So everything's just false here. False, 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 false. And then the logical implication, if P then Q, we know that one. We know that that one is always true, except if P is true and Q is false. So this is going to be true, false, true, true. And then finally, if P and not Q, then C. So now we're going to look at these two as an implication here. And it's another implication. So that thing is always true unless the first one is going to be true and the second one false. So the first one, false, then false, is true. True, then false, that is false. False, then false, true. And false, then false, true. So we did it. We did what was asked of us. And that is construct the truth tables for if P then Q, and also if P and not Q, then some statement that's always false. Right here, notice that they have the exact same truth table. So those two statements are actually logically equivalent to each other. And if we were to prove, say, this last column, if P and not Q, implying that something is always false, then we will also show that if P then Q is going to be also proven. So this is part of the technique in which is involved for proving statements by contradiction. And we're going to see an example of how we do this now. So think what we're really after here. We want to show that if we assume, if we have a statement P, and we have a statement that's not Q, some other thing, negation of a statement. If that happens, then it always implies some false statement. If we show that that can never be true, essentially, then we will have proven the original logical implication if P then Q. So that's all stated right here. Let's look at an example. All right, here we go. Here is a statement we're going to try to prove. For all integers n, if, here's our p, n squared is odd, then n must be odd. So if we have a square of an integer which is odd, then the original integer must be odd. We'd like to prove that. And we're going to prove it by, you guessed it, contradiction. All right, so how are we going to go setting all this up? First, we're going to use the quantifiers that we know of to rewrite the statement. So, what are we saying? For every integer n, and for some other integers, let's say k and w, then n squared is odd. Well, what does that mean? N squared must be 2 times an integer plus 1. That's definition of an odd integer. There's our p. Then n, the original integer, must be odd. Some other odd integer, 2 times an integer w plus 1. So, in quantifiers, we've set this up. And then to prove this by contradiction, we have to show, again, that the conjunction of n squared equal to 2k plus 1, that's your p, and, let me rewrite that a little better, and not q, and that is not n equal to 2w plus 1, so n is not odd and it's going to be even. We have to show that that is always going to be false. Always implying that you get a false statement from that if we say that both of those happen at the same time. If we do that and we show it's always false, then we will have proven the original statement, if P, then Q. So we're going to go prove that now. So what are we doing here? Down again, here's the not Q. If we assume that n is not an odd integer, then it's got to be an even integer. And hence, not Q is really the same as saying that n is some even integer that's just 2 times an integer w here. So that's another way to think of that. And now we're going to go back. Here's the proof right here. Let's go through it line by line. We're going to substitute n into n squared because that's the p part of the statement. And we can plug it in, assuming that n is even. So here we go. Plug in, n is 2 times some integer w, and you square it. What do you get? Well, that's 2 times some integer quantity squared, which is just 4 times an integer squared. But that's also the same thing as writing 2 times w times w, and then 2 times w, since w is assumed to be an integer, that is also an integer, right? It's got to be. And then you have 2 times that integer, which we're just going to say is m here. So this whole 2 times w, we're just going to call 2 times m, where m is w squared. And so really what we get is that, okay, if we square the even, then we get that this is even. That's all it says right here. If n is not odd, that is it's even, then n squared must also be even. What does that tell us? Well, it says that the statement that we're originally trying to consider, P and not Q, right here, I'm circling it in down here, right? If P and not Q, that can never be true. It's always false. Why is it always false? Because we're assuming that n squared is odd, right? And then you say, okay, well then let's just also assume that n is not odd, is even. If we assume that, then it's never true. the conjunction of those two statements. It can never be true because we just showed that if we assume that n is even, then it shows that n squared must be even. But that can't be true because we're assuming that n squared is odd in the statement. So it's always false. What does that tell us? It tells us that no matter what, if we have the square of an integer is odd, then the integer itself must be odd. And this is proof by contradiction because, again, lastly, we just showed if P and not Q, always false. This statement right there, always false. And based on a truth table that we established not long ago, the truth table of that statement, if P and not Q, if that always says you are always false, then that truth table is exactly the same as the logical implication if P then Q. So we show that if P then Q is true by proving the contradiction, and that is take the conclusion of the statement, assume that that is not the case, and then show that the conjunction of P and not Q is always false, which proves the original logical implication. So there's an example on using proof by contradiction. You're basically, the idea is assume something to not be true and show that that can never be true. So that's the idea. And we've had a lot of different videos on proofs, proof techniques. And now we have so many of them, we're going to start venturing into a few more different symbols and concepts before we start proving some statements in the calculus setting. So there you have it. That's it for the video. And now it is time for a short beat so that you can kick back and relax and take a break before you do some more math. All right then, I'm out. Peace.